Hi, and welcome to Midterm 2 Review. So today's topic is going to be asymptotic analysis. We're also going to be looking at trees, binary trees, in which there are BSTs, binary search trees, and also traversals of binary search trees. We'll also be looking at B trees, which include 2-3, 2-4 trees, and their conversion to red-black trees, or also left-leaning red-black trees. And then rotations and color flips corresponding to LLRBs, and then also BFS and TFS, which are traversals for more general graphs, trees. And then we also will be looking at iterators and streams. Okay, so the first topic is asymptotic analysis. So first I want to do some review on some important formulas that might be helpful when doing these problems. So one is written here. 1 plus 2 plus 3 plus 4 plus all the way to n, which is going to result in essentially theta n squared. Another one is 1 plus 2 plus 4 plus 8 plus all the way to 2 to the n minus 1, in which case this is actually going to end up being theta of 2 to the n, so that's going to be exponential. But if your term is supposed to end at, for example, log n, right? So if your summation is from I equals 0 to log n of 2 to the I, then that is 1 plus 2 plus 4 plus all the way to 2 to the log n. And because in general we assume that log is base 2, this is going to cancel out to be n. And so really your summation is from 1 to n, skipping, basically multiplying each term by 2. And so this is going to come out to be theta of n. And so these are pretty useful formulas to know, as well as some geometric sum formulas. So there's the finite geometric series formula, which is a1 times 1 minus r to the n over 1 minus r, where a1 is your first term in the series, and r is the ratio that you're multiplying each term by to get to the next term. And then you also have infinite geometric series, which you probably won't be using much in asymptotic analysis, but it is useful when you have to place an upper bound on your summation so that you get something that's a simpler expression to evaluate. And so in that case, you might be using an infinite geometric series to get the upper bound. So in this case, your sum is just going to be a1 over 1 minus r. So again, a1 is the first term of your series, and then r is really just the ratio that you're multiplying each term by to get to the next term. Okay, so that is all I wanted to cover in terms of good to know formulas, except for one important formula actually, that's for recursive functions. So I guess I can just kind of introduce that while I'm going through these problems. Okay, so if you look at the first one, it's a recursive function, right? It's calling and slam again on n over 2. And so when it's evaluating recursive functions, you want to employ this formula. I equals 0 to depth, or basically height, the summation of the branching factor to the I times the amount of work per node per level. We're already doing it by level, but just kind of emphasizing that. Okay, so basically, to plug and chug into this formula, you really need only 3 pieces of information. You need 1, the height of your tree. Okay, so often for these questions, it's really helpful to draw out the recursion tree. You also need the branching factor, which I'm going to abbreviate from now on as BF, for each node, or more accurately, each node has the same branching factor. And then also the amount of work. Just going to copy that because I'm lazy. Amount of work each node contributes relative, this is an important thing, relative to its input size, relative to its version of n. Okay. And so basically, to kind of restate this formula, right, if I just number all of these based on 1, 2, 3, it's really just I equals 0 to 1 of 2 to the I times 3, right? So this is kind of the overarching formula that we're going to be using in all of these problems. And so let's see how we can apply this to this question. So again, the first step is really to just draw out what the recursion tree looks like. Okay, so I know that I'm going to be starting with an original input size of n, and I know that I'm going to be calling one recursive call with n over 2, and that's going to call one more recursive call with n over 4, and that's going to call n over 8, and all the way down to 1, right? And so basically, we can get the height of this recursion tree by doing how many times can we divide n by 2 to get down to 1, right? So this k is going to give us the height of our recursion tree. So how do we get to this k? We multiply both sides by 2 to the k, so we get n is equal to 2 to the k. And then we need to take the k down from the exponent, and so take the log of both sides. So we get log n is equal to k times log 2. Again, we assume that log is base 2, which means that this is going to become 1. And so we have that k is equal to log n. So in other words, the height of our tree is log n, right? So I'm just going to simplify this to be height is equal to log n. Now, what is the branching factor? The branching factor is 1, because we're making one recursive call per function, right? The amount of work that each node contributes relative to its input size, well, this is really just the amount of work we're doing here, right? So we always want to care about the recursive case rather than the base case, because remember that we care about n as n goes to infinity, right? So the base case is mostly when n becomes really small. So when we analyze for asymptotics, we only care about the recursive case. And so how much work are we doing the recursive case that is not the recursive call? Because again, we're already counting for the recursive calls by drawing this recursion tree and then plugging into this formula. And so really, we only care about the work that we're doing inside the recursive case that is not the recursive call itself. And so that is really just this for loop. And notice that we're just doing linear amount of work, right? So this is just linear, which means that if we plug and chug into this formula, we're going to have I equals 0 to log n. The branching factor is just 1, so that's 1 to the I, so I'm just not going to write that. And then the amount of work per node, per level, is really n over 2 to the I, right? Convince yourself that this is true. When I is 0, which is the root, you're doing n amount of work. When I is 1, which is the child of the root, so n over 2, you're doing n over 2 amount of work, right? When I is 2, you're doing n over 4 amount of work, and so on and so forth. And so if you calculate this, it's really, you can just take out the n in front of the summation. So you get I equals 0 log n, and then 1 over 2 to the I. So you can actually just brutally calculate this part right over here. So if we want to do that, then let's just actually expand out what this would be, right? So we have 1 plus 1 over 2 plus 1 over 4 plus all the way to 1 over n, right? And basically, we can, again, plug it into this finite geometric series formula up at the top. And so it is going to be n times a1. A1 is just 1, so I'm not going to write that. 1 minus r. R is 1/2, right? We're multiplying by 1/2 to each term to get to the next term. So 1/2 to the log n, right? Our n in the formula is actually log n. And then divided by 1 minus r, which is 1 minus 1/2. Okay, so if we expand this out, the denominator is going to be 1/2. Flip that, so it's going to be n times 2 times 1 minus, now it's 1/2 to the log n, right? And so if you think about this, 1/2 to the log n, I'm just going to write it at the top because I'm kind of running out of space here. So this is equal to 1/2 to the log n, right? Which is really just equal to 1 over 2 to the log n. And we said that we can assume that log is base 2, which means that this entire denominator is just going to be n, right? And so this is just 1 over n. Yeah, and so this is going to be n times 2 times 1 minus 1 over n. Okay. And so if you basically simplify this, we have n times, I guess we could just expand it out, right? 2 minus 2 over n. And then this is just 2n minus 2. If you really want to be very detailed with the math and expand out everything. So this is really just theta of n. And notice that this is both the worst case and the best case, because really there's no way for us to bypass anything in the function. We have to execute every single part, right? So this is both the worst case and the best case. Also, another thing that you can just realize is that one thing that you can do instead of doing all this calculation every time is do a little simplification at this step. So notice that this is always going to be upper bounded by n times the summation from I equals 0 to infinity of 1 over 2 to the I, right? And so we said that the formula for an infinite geometric series is this one, right? A1 over 1 minus r. So what is that? Well, again, the summation is going to be 1 plus 1 over 2 plus 1 over 4 plus 1 over 8 plus all the way to 1 over n. It's capital N, right? And so if we plug in a1 over 1 minus r, a1 is just 1 minus r is 1/2, right? And so that is really just 2n, right? Which is equal to theta of n. So basically we're saying that this quantity here, right, is less than or equal to theta of n. So again, this is why we can actually employ this infinite geometric series formula to kind of simplify our expression. But either way, it gives the same result. All right. Oh, and I did not realize that I had extra space, so let me just put it out. Okay, so now on to question 2. So give the running time for this function. Hopefully you're stopping yourself and looking at the question before you actually see the answer. But n is going to represent now the length of an array. Okay, so it's kind of important to kind of parse the different things that we're doing in this function. So we're doing a constant amount of work with printing, so we can actually just ignore this. I just like to cross out things that are not going to affect our runtime too much. In other words, constant runtime. And then we're looking at this for loop, right? So we're going from low to high, and we're printing out something. So this is a constant amount of work inside the for loop. So really, the whole runtime of this for loop is equal to the number of iterations, right? And so notice that first we pass in low and high as 0 and n respectively, which means that the first time we're going to be doing a linear amount of work. So keep that in mind. And then we're doing another printout, right, which is constant amount of work. And then we have if high minus low is greater than 0, we have this random number. And if it's greater than 0.5, then we do one recursive call. Basically, if I want to draw out visually what this function is doing, although it's not really necessary for you to have a good understanding of what the function is doing. Basically, it's taking the middle value, right? High minus low divided by 2, right? So this is like kind of the mid. And so this, this first recursive call is just basically passing in this part of the array, right? And so is this one. But then the second one is basically passing in this part of the array, right? So kind of like binary search, I would say, but it's a little bit more complicated than that because it depends on this random coin value. But anyway, so you can kind of see that there's a different best case and worst case here depending on what the coin random value is, right? So the worst case is probably when we have to do more recursive calls, right? Which is going to be the else case. We have to do 2 recursive calls. And the best case is when we just have to do 1. So let's actually take the best case first because that just seems a little bit simpler to me. Okay, so I can just do it here. So in the best case, right, we're doing 1 recursive call, and basically we're splitting the array in half, right? Remember the diagram I just erased? We're just passing in the